The Himalayas have always been one of the most unforgiving places on Earth to build infrastructure. Towering cliffs, fractured rock formations, and deep gorges turn every project here into an extreme engineering challenge. But right in the middle of this terrain, India built the Anji Khad Bridge, the country's first cable-stayed railway bridge. What makes this bridge special is that it was not originally designed as a cable-stayed bridge. The first plan was to build a steel arch bridge. But after geological surveys, engineers discovered that one side of the mountain slope was too weak to withstand the enormous horizontal thrust generated by an arch structure. As a result, the entire design had to be changed. Instead of relying on both sides of the gorge, engineers built a 193-meter-high concrete pylon and used 96 steel cable stays to suspend the bridge deck across the canyon. So why was the arch bridge design abandoned? And how did engineers manage to build an asymmetric cable-stayed bridge in the harsh terrain of the Himalayas? We'll find out in today's video. Before we begin, don't forget to hit like and subscribe to support this video. Thank you so much. Now, let's get started. To understand why the Anji Khad Bridge has such a special design, we need to look at the overall project. This bridge stretches across the Anji River, located in the rugged, mountainous region of Jammu and Kashmir. It is a key component of the Udhampur-Srinagar-Baramulla Railway Mega Project, also known as USBRL. The main goal of this railway is to cut through the Himalayas, connecting the Kashmir Valley with India's national railway network. The construction requires engineers to guide the railway tracks over gorges, hundreds of meters deep. According to the initial plan, while surveying the Anji Gorge, the project management board decided to use a steel arch bridge design. In terms of structural mechanics, an arch bridge is the most optimal choice to cross narrow and deep valleys. Its working mechanism is very clear. The entire load of the bridge deck structure and passing trains is transferred along the curve of the arch, then pushing the horizontal thrust directly into both sides of the mountains. However, this option has a mandatory technical requirement. Both mountainsides must be solid, monolithic rock formations with an extremely firm structure to withstand the massive pressure from the two arch footings. And this is when the problem appeared. When the geological survey teams drilled deep into the bedrock at the Anji Gorge, they obtained a result that forced the entire project to halt the old design. The core sample analysis showed that the geological structure at the Anji Gorge is inconsistent. Specifically, the mountainside towards Katra is made of crushed, fractured slate seams, containing many tangled deformation zones. The rock density here is too low and does not meet the standards for load-bearing capacity. If they continued building according to the old blueprint, the horizontal thrust of thousands of tons transferred from the arch structure and the weight of the trains would shatter the bedrock, leading to the risk of landslides and the collapse of the entire structure. To solve this problem, engineers could not change the route's location, but absolutely had to change the bridge's load transfer mechanism. The final solution proposed was an asymmetrical cable-stayed bridge using a single pylon. Why an asymmetrical structure and using only one pylon? Analyzing the geological cross-section, the opposite mountain slope has a much harder and more stable rock foundation. The engineers took advantage of this to shift the entire load-bearing center of the structure to the hard rock area. They designed a main reinforced concrete pylon reaching 193 meters high, anchored directly into the stable mountain slope. From this single pylon, a network of 96 high-strength stay cable bundles is deployed to suspend the bridge deck reaching across the gorge, without needing to place any supporting pillars on the weak rock side. The asymmetrical design works on the principle of static counterweights. The anchor cable system pulling backward behind the pylon creates an opposite pulling force, completely neutralizing the downward sagging pull from the main span. This design helps the bridge balance its own load, without relying on the weak cliff on the opposite side. But determining the new structural design was only the beginning. Because there was almost no direct access to the site, all heavy equipment and construction materials had to be transported into the work area using specialized lifting and transport systems across the steep mountain terrain. Once the construction site was fully established, work on the foundation officially began. The method used here was step-by-step excavation from the top down. Excavators continuously removed layers of rock to create working platforms, while drilling rigs drove deep steel anchors into the mountainside to stabilize the surrounding geology. Immediately afterward, high-strength concrete was sprayed directly onto the exposed rock surface to reinforce the entire construction area. This process of excavate and reinforce continued repeatedly until the required depth was reached. At the bottom of the foundation pit, a series of drilled piles were installed deep into the solid bedrock to eliminate any risk of slope failure. Finally, thousands of cubic meters of concrete were poured to create a massive foundation block firmly locked into the mountainside. Once the foundation was complete, the next challenge was constructing the 193-meter tower above the Himalayan canyon. At this height, building traditional scaffolding was nearly impossible. Instead, engineers used a self-climbing hydraulic formwork system. After each concrete pour, powerful hydraulic cylinders pushed the entire formwork system upward, preparing it for the next section of the tower. Meanwhile, workers had to operate high above the ground to install and tie together the dense steel reinforcement inside the tower. This cycle of steel installation, climbing formwork, and concrete pouring continued repeatedly until the tower finally reached its full height of 193 meters. But the most difficult stage of the project only truly began after the tower was completed. How do you extend a steel bridge deck weighing thousands of tons across a deep canyon with no support underneath? The first stage involved hydraulic launching. Steel segments were assembled near the base of the tower, then slowly pushed outward into open space to create the first cantilever section of the bridge deck. Once the temporary structure became stable enough, the derrick crane began operating. One by one, new steel segments were lifted off the ground, moved out over the canyon, and carefully aligned before being temporarily locked in place with high-strength bolts. But those bolts were not the final load-bearing connection. As soon as each steel segment was secured in position, a cable from the top of the tower was lowered and tensioned to officially take over the full load of the bridge span. Only after the cable system became fully stable did permanent welding begin. Meter by meter, the bridge deck slowly extended across the canyon until it finally connected with the opposite cliffside. After the main structure was completed, a specialized railway track system and vibration dampers were installed to control movement caused by strong Himalayan winds and passing trains. The final stage was full-scale load testing. Heavy trains weighing hundreds of tons were sent across the bridge to measure deck deflection, vibration, and the load-bearing performance of the entire cable-stayed system. Only after the structure returned to a perfectly stable condition under testing did the bridge officially pass its final engineering challenge. In 2024, the first train officially crossed the Anji Canyon. That moment marked not only the completion of India's first cable-stayed railway bridge, but also the final and most technically complex piece of the entire USBRL mega project. Once again, modern engineering proved that even the harsh terrain of the Himalayas could not stop humans from connecting places once thought impossible.